This video is the lecture notes for determinants in inverses, where we will be finding determinants, inverses, and then using Cramer's rule to solve systems of equations. On our first page of notes, first thing we want to do is to talk about a non-singular square matrix, meaning that if it's a non-singular square matrix, that means it's going to be a square matrix and that the determinant of that matrix will not equal to 0. Notice that we can write determinant of matrix A in this format. So in order to find the determinant of a 2 by 2 matrix, let's start off with, if we had a 2 by 2 matrix, we'll call it A, B, C, and D, then the determinant of that matrix, we can write it like this. We can also write it like this in terms of having A, B, C, and D like this. And what that means is that we're going to find the determinant of A by multiplying A times D and subtracting B times C. So if you think about it, you're going to do like a diagonal multiplication, A times D, and then you're going to subtract B times C. So this is going to give us a number. And we got to make sure that that number does not equal to 0. If it does equal to 0, then it's singular. If it doesn't equal to 0, then it's non-singular. So let's try our hand at finding the determinant of this matrix here, for example, number 1. You might want to pause the video here and try it on your own. So if we're trying to find the determinant, we were going to multiply 3 times 1 and subtract the multiplication of -2 times 6. Do the math here, we'll get 3. These two become a positive, so it'll be plus 12, and the answer here is 15. Now, in order to find the determinant of a 3 by 3 matrix, we're going to have to do some more creative math. First, let's find a 3 by 3 matrix. So we're going to use the matrix 2, 1, -1, -1, 2, 4, 1, -2, and -3. So we want to find the determinant of this 3 by 3 matrix. The first thing we're going to do is rewrite the first two columns. So I'm writing these in blue so that you can see that these are the same as this column here and as this column here. So I wrote those. So the first two columns were rewritten right here. The next thing we're going to do is we're going to multiply diagonally up and diagonally down. So let's do these first. We're going to multiply these three numbers together. So when I multiply, I get 4 times a -3, that's -12. Then I'm going to multiply these three numbers together. That's the 1, the 4, and the 1, and that's going to be 4. And then I'm going to multiply these three numbers together. So that's -1 times -2. That gives me -2. And then I'm going to add these numbers. When I add these numbers, I'm going to get -10. If you want to think about this as like the major numbers. Why do I call them major numbers? Because these are going down the main diagonal. So now let's see about going upward, multiplying upward. So when I multiply this way, I have the number 1, 2, and -1. That's going to be -2. Then I'm going to multiply these three numbers. So -2 times 4 times 2. That's going to give me -16. Then I multiply these last three numbers. I'm going to get -3 times -1 times 1, which is 3. And then I'm going to add these numbers. When I add these numbers, I'm going to get -15. So to find the determinant of our matrix, we're going to get the major numbers that we have right here. So I'm going to write it like this. Our major numbers, and we're going to subtract the minor numbers, if you want to call it that. Minors meaning that these are diagonals, but they're less than the major ones, right? The major ones are going from the top going down, the minor are going from the bottom going up. So we'll call these guys up here the minor numbers. So in our case, we're going to get our major numbers, which is negative 10, and we're going to subtract the minor numbers, which is negative 15. Notice that it actually becomes a positive 5. So the determinant of matrix B is equal to 5. So let's see about some information regarding inverses of matrices. If a square matrix is non-singular, which we know what that means now, that means that the determinant of some matrix does not equal to 0, then we can find the inverse of that matrix. So there's a couple of ways that we can find the inverse of a 2 by 2 matrix, but I'm going to just show you one, because if I show you this one, you could also do it for a 3 by 3 matrix and a 4 by 4 matrix. If I showed you the other little shortcut, it only works for 2 by 2 matrix. So that one you can probably learn on your own. So let's go find the inverse of matrix A, when we'll call matrix A, little b, little c, little d. And what we want to do is we want to get our matrix, and we're going to put it in an augmented matrix, and the augmented it with the identity matrix. Remember, an identity matrix for a 2 by 2 looks like this. We're going to use row manipulation to get our matrix A and our identity matrix to actually switch places. In other words, we're going to go find our identity matrix on the left, and we're going to have our A inverse on the right. So let's start off with a 2 by 2 matrix. We'll call matrix A 3, -2, 6, and 1, which we already know the determinant of this one. We solved it earlier. So we know that it is a non-singular matrix. So we're going to augment it. So I'm going to have 3, -2, 6, 1, and I'm going to have augmented my identity matrix. So now what we want to do, remember that we want to get this guy right here to be a 1. So what we did before is we multiplied everybody in row 1 by 1/3. So that's going to give me the matrix of 1, -2/3, 1/3, and 0. So notice I have to go all the way across that row. Notice the second row did not change, so I am going to write down the second row. The next thing we want to do is we want to get this one to be a 0. So what I'm going to do is I'm going to multiply the top one by -6 and add it to the bottom row. Notice the top row doesn't change, so I'm going to write that down. The bottom row I'm going to multiply by -6 times 1 and then add it, and I'm going to get 0. I'm going to multiply by -6. Remember, we're going to get a +4 and add it to the 1. I'm going to multiply by -6. I'm going to get a -2 and add it to the 0. Multiplying by -6 times the 0 and adding to 1, and I'll get my 1. So the next thing we need to do is to get this to become a 1. One of the fastest way to do that is to multiply by 1/5 to the second row. So the first row stays the same as 1, -2/3, 1/3, 0. And the second row, I'm going to multiply everybody by 1/5. So I'm going to get 0, 1, -2/5, and 1/5. We're almost done. The last thing we need to do is get this guy to be a 0. So we're going to multiply the second row by +2/3 and then add up. So we're on our last matrix. The bottom row doesn't do anything, so it's going to be 0, 1, -2/5, 1/5. The top row, I'm going to multiply this times 2/3 and get 0 plus 1. I'm going to multiply and get 2/3 and add that and get 0. Multiply, oh, here's some math. So we're going to get -4/15, and we're going to have to add it to the 1/3. Remember, 1/3 is the same thing as 5/15, so when I add them together, I get 1/15. Multiplying 2/3 times 1/5, I get 2/15, and then I just have to add 0, so I still get 2/15. I'm done, because on this side I have the identity matrix, so this must be A inverse. So I'm going to write down that A inverse is equal to the matrix 1/15, 2/15, -2/5, and 1/5. One way we can check our answer is to multiply A times A inverse, and I should get the identity matrix. So on the next page of our notes, let's go find the inverse of matrix B. So the first thing we need to do is to augment our matrix with the identity matrix. Now that we've done that, we need to do row manipulation so that we get the identity matrix on the left, and on the right side we'll have B inverse. So from here you can pause the video and try to do it on your own. You can also follow along on this video. So the first thing we need to do is get a 1 right here in the 1, 1 position. So I am going to switch row 1 and row 3. Because row 2 is the only one that doesn't move or change, I wrote that one down first. Now we're ready to get zeros underneath that newly found 1. So I need a 0 here in the 2, 1 position and a 0 here in the 3, 1 position. So the first thing I'm going to do is add to the second row, and that will get this 0 here. Then I'm going to multiply by a -2 and then add it to the third row. So notice the first row is the only row that doesn't change. So I'm going to write that one first. Now I'm ready to change row number 2 and row number 3. Now we need to get a 1 right here in this position, and notice I have a 0 here, but I have a 1 in the position over here, so I'm going to switch row 2 and 3. Notice that the only row that does not change is row number 1, so I'm going to write row number 1 first when I get started on my new matrix. Now I'm going to switch row number 2 and row number 3. Now I need to get a 1 in this position, so what I'm going to do is to multiply row number 2 by 1/5. Notice that row number 1 and row number 3 don't change, so I'm going to write those first. Now I'm ready to change row number 2 by multiplying every term by 1/5. So now we have 1, 0, 0. I have a 1 in the 2, 2 position, so I need to get a 0 below it and a 0 above it. So I need to change this to a 0. So I'm going to multiply row number 2 by 2 and then add up to row number 1. So notice row number 2 and 3 don't change, so I'm going to write those first. Now I'm ready to multiply times 2 and then add to the 1. Multiply and get 2, add to the -2 to get 0. Multiply, get 2, add it to the -3 to get -1. Multiply times 2, I'll get 2/5 and add it to 0, so it would be 2/5. I'm going to multiply times 2, which is 0, and then add it to 0. Then I multiply 2 times the -2/5 is going to be -4/5, and then I have to add it to the 1. Remember, 1 is the same thing as 5/5, so when I add it, I get 1/5. So now I have a 1 in the 3, 3 position, so I need to get a 0 here and a 0 here. So for row number 1, I just have to add row number 3 to row number 1. For row number 2, I'm going to have to multiply by a negative and then add to row number 2. So my last matrix, the only thing that doesn't change is going to be the bottom row. So I'm going to write that one first. And then now I'm going to multiply and add to change row number 2. So I multiply by -1, I get 0, and I add. Multiply by -1, I get 0, and I add. Multiply by -1, and I get -1, and I add. I multiply by a negative, which is 0, and I add to 1/5. Then I multiply, I get -1, and I add it to 0, so it's -1. I multiply, I get -1, and I need to add it to a -2/5. So remember, this is 5/5, so I get -7/5. All right, the last row, which is our top row. So I'm going to just add. So 0 plus 1, 0 plus 0, 1 plus -1, 0 plus 2/5, 1 plus 0, and 1 plus 1/5 is going to give me 6/5. Alrighty, so I'm going to go on ahead and put my augmented matrix, and what we have found is B inverse. So inverse matrix of B is this 3 by 3 matrix of 2/5, 1 6/5, 1/5, -1, -7/5, 0 1 1. So let's use this inverse matrix. So if we're given a 3-equation system and we need to solve it by using the inverse matrices, notice that we need to get our coefficient B, and we also need B inverse. So remember, when we write this system, we're going to write it as matrix B, which is our coefficient matrix, and then we're going to have our variable matrix, which is X, Y, and Z, and then we'll have our answer column, which is 3, -3, and 4. So now this is matrix B. If I multiply it times the inverse of its matrix, I'm going to get the identity matrix, and then I'm going to multiply that times our variable matrix, and that's going to be our answer column. But remember, our answer column needs to be also multiplied by B inverse. So if you want to find X, Y, and Z, you got to get B inverse, which is what we found above. So I'm going to write down B inverse. And I'm going to write down our answer column next to it so I can multiply. And then now I'm using matrix multiplication. Remember, this is a 3 by 3 matrix. This is a 3 by 1 matrix. So our answer will be a 3 by 1 matrix. And we need to multiply these two matrices together. So just a quick refresher. Remember, you're going to multiply row 1 times column 1. So I'm going to have 2/5 times 3 plus -3. That's 1 times -3 plus 4 times 6/5. So I showed my work down here so that you can see I'm multiplying and adding, and I got the common denominator for all 3 numbers. Then I added all the tops, and that's how I got 15/5, which is the same thing as 3. So now I'm ready to do the second row times our column. So I'm going to get 3 times 1/5, and I'm going to plus -3 times -1, so that becomes a positive 3, plus 4 times -7/5. So again, I'm going to do the same thing, getting everybody with the same denominator so I can add them together. And here we find our answer is -2. And then now we're ready to do the last one. We're going to multiply the last row times our column. When I multiply, I get 0. When I multiply, I get -3. When I multiply, I get 4. So -3 plus 4 is 1. So we can see that this is going to be a consistent and independent system with our solution set at the point 3, -2, 1. And that's how we write it in curly brackets. Alright, so that should fill up another page of notes. Let's go on ahead and go to Cramer's rule. So far what we've done is we have found the determinants. As long as the determinant doesn't equal to 0, we can go find the inverse. Okay, so now let's use our determinants to our advantage by using Cramer's rule. So the very first thing we're going to do is we're going to go find the determinant of our coefficient matrix. And I think we already worked this in one of our examples, so we can do it again for practice. So I am going to do that for practice and remind you that the way we did that was to rewrite the first 2 columns. So multiplying diagonally down, I get a negative 12. Multiplying diagonally down, I get a positive 4. And when I multiply diagonally down, I get a negative 2. So we can see that this is going to equal to negative 10. When I multiply going up, I get a negative 2. When I multiply going up, I get a negative 16. And when I multiply going up, I get a positive 3. I'm going to add them all up together, and I end up with a negative 15. So we get our majors subtracting our minors, so we get negative 10 minus a negative 15. And that's how we get 5. So we find that D is equal to 5. That's the determinant of the coefficient matrix. So the next thing we're going to do is go find dx. So for dx, what we're going to do is we're going to get all the column that has all the x coefficients, and we're going to replace them with our answer column. And everything else stays the same. And now we got to go find the determinant of this one. So I'm going to go on ahead and do the math so that you can see that I am finding the determinant, but you might want to pause here to see if you can find the determinant on your own. So what we found when we multiplied the majors, we got a negative 8 when we multiplied and added. For the minors, we got a negative 23. So I'm going to have negative 8 minus a negative 23. Remember, that becomes positive. And we're going to find that dx is equal to 15. Then we're going to keep on going. Now this is the cool part. If you want to find what the value of x is, you get your dx and you divide it by d. So you're going to see that x is going to equal to 15 divided by 5, which means x is going to equal to 3. So we have found the x value. We're going to do the same thing for the y. So the first thing we're going to do is to go find dy. So remember, to find dy, we're going to find the determinant of a 3 by 3 matrix where our answer column takes the place in the middle for our y values. And everybody else stays the same as our coefficient matrix. And then we're going to find the determinant of this one. So I'll let you do the math on your own, and you should find that this is equal to negative 10. So we find that dy is equal to negative 10. If you want to know what y is, you got to get dy and divide it by d. So we're going to get negative 10, and we're going to divide it by 5, and we're going to find that y is equal to negative 2. Similarly, we do the same thing for dz. Again, remember, you're going to get your answer column, and you're going to put that where the z's go. And then the other two columns remain the same as the coefficient matrix. You're going to go find the determinant of this one. And you can find that if you know dz is equal to 5, then you know z is equal to dz over d, or 5 over 5, which is 1. So we can see that this is a consistent and independent system that we've already solved before, which is 3, negative 2, and 1. And that would be our answers. And that concludes this video.